This week we're going to start to look at how we actually compute some statistics. So this is going to be a little bit more mathematical than the last couple of sections that we've looked at. So as a reminder, a statistic is just a single number that is meant to describe or summarize an entire data set. So let me write this down really quickly. A statistic is a number that summarizes a data set. And so there's different ways that we can try to summarize the data set. In this case, we're going to be looking at measures of center, numbers that try to summarize or boil down where the middle of our data set is. And there's going to be three measures of center that we look at. You'll probably be familiar with at least one of these. The mean, which is often just referred to as the average. So we're going to look at the mean. Another measure of center we'll look at is the median, which you may have also heard of. And lastly, we'll look at the mode. So we'll look at all three of these. So let's start with the mean. This is probably the most common one, the one that most of you will have heard of. And again, another word for this is just average. And you may even know exactly what a mean is and how to compute it. How to find the average of, say, two numbers. If you're trying to find the average of two numbers, you add up those two numbers and you divide them by 2, and it sort of gives you the halfway point between those two numbers. More generally, if we're trying to find the mean, we have a general formula, and it's basically if we have a long list of numbers, we want to sum up all of those numbers. So all the numbers in our data set. And then I want to take that and divide it by the number of numbers, or the number of values. Let's use the word values. No, let's use the word numbers. That's fine. And this is sort of the general formula. We are going to introduce some notation that'll make this a little bit easier to write out. And it's notation that we're going to use for the rest of the semester. So these symbols that I introduce here, you will see these symbols again. So before we do that, I want to do two things. I want to define sort of the two different contexts that we're going to be able to see these things in, and then I also want to go through the notation as well. So we will have a mean in the context of a sample. And we will also have the mean in the context of an entire population. And so I'm going to write that down here, and let's write out what both of these wind up looking like. So if the data that you're dealing with, the numbers that you're dealing with, are part of a sample, and you want to find the average of that, then we are finding what's called a sample mean. If those numbers make up the entire population and we want to find the average of them, then we're looking at what's called a population mean. We're going to have different symbols to represent these two things. So when we talk about a sample mean, what we're going to do is use the symbol of an X with a little line over the top of it, and I'll call it X bar. So this is the symbol that means sample mean. When we're talking about a population mean, we're going to use a different symbol, and that symbol is going to be the Greek letter mu. And it basically looks like a little lowercase u with kind of a tail on the front. So basically, if I write a lowercase u and then put a little long tail on the front, that's what we're doing. Oops. So there's the Greek letter mu. So it's written mu, and it's a Greek letter. This thing I will refer to up here as X bar. So throughout the semester, these are the terms I'll use. When I'm talking about X bar, I'm talking about a sample mean. When I'm talking about mu, I'm talking about a population mean. And to compute these things, what we'll do is follow this formula, but I'm going to use some shorthand notation. The first thing I'm going to use is this symbol. This symbol is the Greek letter sigma, and it means that we're going to sum a bunch of stuff up. So I'm going to write this sigma x, and it means sum up all of the x values that we have, where the x values are the actual data pieces in our sample. So this symbol here is the Greek letter sigma, the capital letter sigma, and it means sum stuff up. So take the values and sum all of them up. And this is what we're summing up. What are we supposed to sum up? These are, in this case, all of our sample values. So all of the data set that we have in our sample. And lastly, we will divide by, in this case, the letter lowercase n. And the letter lowercase n is meant to be a placeholder for our sample size. So we've used this in a previous section. We used n when we were talking about a sample of size n. This lowercase n is going to be a placeholder. We'll use it for the rest of the semester whenever we're talking about a sample size. So this is the formula. It's x bar equals the sum of all the x's divided by n. This is a shorthand way of writing what we wrote in words up here. The formula for the population mean is very similar. We're still going to add a bunch of stuff up. So I'm going to start with that. Oops. I'm going to start with that summation symbol, or the thing that I called sigma up here. And it's kind of like a spiky backwards 3 or a weird spiky E, letter capital E. Same thing. We're going to sum up all the values, and then we're going to divide by the total number of values that we were dealing with. And in this case, I'm going to use capital N when we refer to the population size. So this represents the population size. And again, now these x values, instead of representing values from the sample like they did up here, these are now the different population values that we're adding up. So hopefully this makes some sense, and if it doesn't, let's do an example so that it can become a little bit more concrete. Okay, so let's say we're looking at a set of exam scores. And we want to find the mean of this set of exam scores. So in this case, maybe those exam scores are an 80, an 89, 94, 77, and an 85. Okay, so these are all the values. If we want to find the mean, the first thing we need to figure out is, so that we can use the correct symbols, is which of these two contexts makes more sense. Is this a sample or is it a population? Typically in a problem, they'll actually tell you this data set represents an entire population or it represents a sample. And other times we'll have to kind of figure out based on context. In this case, there's only 5 exam scores. That would be a very small class if it were the entire population. So I'm going to assume that we're talking about this being a sample. So this is a sample from a larger class, which would make some sense. Okay, so in that case, that means that we're dealing with x bar, our sample mean. And to get this, we need to sum up all the values and then divide by the number of values. In this case, we said there are 1, 2, 3, 4, 5 total numbers. And I need to add them up and then divide by 5. So 80 plus 89 plus 94 plus 77 plus 85. And you can do this on a calculator. I'll also down the line show you how to do this on both a graphing calculator and also in Excel. I can show you how to find the mean in both of those things. So we add those up on top. If we're doing it in a calculator, I added them up and I got 425. and we're dividing that by the same 5 that's on the bottom. And when we do that division, I wind up with 85. So the mean score, the middle of this data set, is an 85. That just so happens to be one of the numbers that's in this particular list, but in general, this number that you get spit out for the mean doesn't actually have to be one of the values that's sitting here. It's also possible that different exam scores could lead to the same mean. So, for example, if same thing, we had other exam scores, and those other exam scores were maybe a 60, a 62, a 100, a 103, and another 100. Maybe there's extra credit on this exam. If I add those numbers up, and again, they represent probably a sample in this case. Let's just assume that they represent a sample. So 60 plus 62 plus 100 plus a 103 plus another 100. And I'm dividing those by 5 because, again, it's 5 scores. And if you add those up, you'll actually see that they wind up adding up to the same total as before, and we wind up getting the same mean. The reason I'm showing you this is we can have two sets of exam scores with the same mean, even though those sets of exam scores look very different from one another. And this is kind of the idea behind these statistics. They're going to summarize the data, but because we're summarizing it, we're necessarily going to be leaving out some important information. We can't reconstruct the entire data set based on this one number. So in this case, it looks like most of the numbers are kind of clustered, kind of in, at least in that ballpark, close to 85, whereas this one, none of the scores are near 85. We have some scores that are way higher than the 85, and we have some scores that are way less than the 85. And so later on in the next video, we'll talk about how we can capture this kind of a discrepancy. Over here, the scores seem to be much more clustered together. Here, they seem to be much more spread out. And in the next video, we'll be looking at measures of spread, which will capture the effect that I'm talking about here. But for now, this is the idea of the mean. I want to give you one last kind of thing to think about, a way to think about how these things work. Let me get rid of this here. I don't want to invite someone. Close that down. There we go. Okay. So one other way that you can think about it, or you can kind of interpret what the mean is the following. The mean can be thought of as sort of the fulcrum on like a teeter-totter, some sort of balance. So if you imagine that we've got like a number line, and this is where the numbers are. If we put, okay, here's one number, here's another 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 number. Whatever the case may be, if these represent numbers on a number line. So hypothetically, you'll remember number lines work from left to right, smaller numbers on the left, larger numbers over here. So maybe this is, you know, this is like 60 way over here, and this is that 103 way over here, or something like that. Obviously, I'm using a different set of numbers here. But if we did this, what you would wind up seeing is maybe the balancing point that would get this teeter-totter to balance would be right here. And this balancing point is where the mean would fall. So the mean is, the mean can be thought of as the balancing point in our set of numbers. So this is a good way to think of what we mean when we say the center. It's sort of the balancing point in the middle of all of the data. Okay, so let's move on to the next topic, which is going to be the median. And the median is, again, it's another measure of center, but it is essentially the middle number in an ordered list. Okay. There's no symbol that we're going to use for this, right? There's no x bar, there's no mu. None of those symbols apply to this. We will just write the word median out when we're talking about this. In the calculator, you may see this shortened to just be the letters MED for median. So MED would be another way of symbolizing the median. If we go back to our example that we had a minute ago, the exam scores, the first one where the scores were 80, 89, 94, 77, and 85, to find the middle number, I can't just say, oh, here's the middle, and that must be our median, because this list is not ordered. We haven't sorted it, so this is the wrong answer. That's the wrong approach there. Oops. So how do we do this? The first step is to order the list. And that means we'll go from smallest to largest. So if I reorder these, the smallest is the 77, then comes the 80, then the 85, then the 89, and then the 94. So now they're in order from smallest to largest, and now I can say, oh, here is the middle. This number right here is the middle, it's our median. So in this case, the median is equal to 85, and it just so happens to be the same value that we got for the mean. That doesn't always necessarily happen. In fact, we'll talk about comparing these numbers down the line. So just keep in mind, you're not always going to get the same number. Another question is, what happens if in our list of numbers, how do we find the middle, right? I use this word middle, and in this case it was really obvious just by observation that this is the middle. But how do we find it in general? Like, what if there were, so we had 5 numbers, what if there were 6? What if there were 6 numbers? Then suddenly the middle, right, if I add in another number, maybe there was also a 96, and now there's 6 total numbers, where's the middle of this list? Well, now the middle would be somewhere between these 2 sets of numbers, and this would be our median. And I would have to find the halfway point between 85 and 89, which would be, in this case, 87. I can kind of find that by observation. But otherwise, you have to average these 2 numbers together. You have to find the mean of the 85 and the 89 to find the halfway point between them. And that would give us this for our median. But again, so all this blue stuff assumes that this number 96 had been tacked on. So there's a different approach. But what if you have a really long list of numbers? How do we figure out the middle if our list has hundreds and hundreds of values in it? It's not going to be as easy to just by observation say, oh, this is sort of the middle of our list. So what do I mean by the middle? How do we determine the middle? We talk about the middle. How do we figure out what the middle is? That is a question. Okay, so I'm going to give you an approach that we can use, and we'll wind up using this approach down the line in another section towards a couple videos from now. So I want to introduce it here, and then we'll kind of recycle this approach in a couple of videos for another type of problem that we're going to look at. So to determine where the middle was, I want to start with that list of numbers that we had up there and just go through it a little bit more carefully. We're not just going to figure out the middle by observation this time. So 80, now let me do the sorted list. My bad. So 77, 80, 85, 89, and 94. And let's forget about that, that 96. Let's pretend that wasn't there for now. What I'm going to do is I'm going to number each of these as basically which position in the list they fall in. And I'm going to use the letter L, capital L, to represent the position of each of these. So this is at position 1, position 2, position 3, position 4, and position 5. And you'll notice this number right here is N. It's our sample size. there are 5 things in this list. So we determine the middle of the list by looking at these numbers, the L's. Forget about the original set of numbers, the 77, 80, and so on. Just think about the 1, 2, 3, 4, and 5. I want to figure out where the middle number is. And by observation, the middle number is sitting here at the 3rd position. So I want to somehow figure out how to get 3 out of a list of 5 numbers. And the way that we do it is the middle occurs halfway through the list. And when I say halfway, that means we can think of that mathematically. So the middle occurs at the halfway point. And when I say the halfway point, I mean L is going to be approximately, I'm going to take n and divide it by 2. Take half of the value of n. And in this case, when I take n over 2, in this case n was 5, that would give me 2.5. So 5 divided by 2 is 2.5. But there is no 2.5 position in the list, and instead I have to round up to, in this case, 3. So let me do that for us. So for us, it was 5 over 2, which is 2.5. We had to round up to 3. And that gives us the correct position of the number that we should be looking at. What would happen if we did have that extra number tacked in? Well, now this number right here, let me just move this. Just move this right here. This would be at the 6th position. So this was our n before. This is our new n if we're including that 6th number. And what would the middle be there? So in that case, L is going to be, again, the same thing. We'll do n divided by 2. But now as n would be equal to 6. And we would get 3. And that would tell me, okay, this is the middle number because it's at position 3. But if you look at it, this isn't the middle number in the list that includes the 96. The middle number would be actually, as I mentioned a minute ago, between the 3 and the 4. So in this case, instead of rounding up, we wound up getting a whole number out of this. We want to average this number with the value at the next position, which is, so if we called this first one L, the next position will be L plus 1. So in this case, that would be position 3 is the value of L that we just found, and position 4 would be the L plus 1. So I want to find the average of the two values associated with 3 and 4, so the 85 and the 89. And that's how we would get our middle value in this case. So at L, we got 3, L plus 1 in this case would be 4. The numbers we got for each of these were 85. That was at position 3. And at position 4, it was 89. The halfway point between these we can get by adding them together, 85 plus 89 divided by 2, and that would give us the 87, and that would be our median. So you'll notice we can do this. We kind of have these two different approaches. This first approach will work whenever, where we just round up, that'll work whenever n is odd. So if n is odd, we'll always wind up with a decimal here, and we'll always round that decimal up. If n is even, then we'll always get a whole number. Whenever we wind up with a whole number, you can't just look at the value at that whole number. You have to look at the value at that whole number plus the next value in the list. So not just at 3, but also at position 4. So we have two different rules. If n is odd, we do one thing. If n is even, we do another thing. This is how we find the median of our list. So hopefully that makes sense. The last one I want to talk about the last measure of center I want to talk about is the mode. So the mode is a third measure of center, and it really is typically reserved for when we're dealing with sort of visualizations of the data. The mode is the most common, or another way to say that would be the most frequent. Let me just write the word out, or frequent value in our list or in our data set. So if we have a histogram for our data set and it looks something like this, this is the mode. We already used this terminology before. The mode is the peak of our data set because this would be frequency on this. Here would be our values down here. And the most frequent value is the one that has the highest peak. So this is just the highest peak in our histogram. And it's the value associated with that highest peak. So whatever number would be sitting down here, that would be the mode. Whatever number has the highest peak. So for example, if I did a quick list of data here, maybe our list looks like 0, 0, 1, 1, 1, 2, 2, 3, 3, 3, 3, 4, 4, 4. Put commas between these. Here's our big long list of data that we found. We'd notice what is the most frequent value. I've already ordered them so it's easier to spot when they're all grouped together like this. And it looks like 3 occurs more than any other number. So in this case, the mode, and again, there's no special symbol for this, the mode is going to be the number 3. And we would see that very clearly if we tried to graph these in some sort of histogram. Or a bar graph. 0, 1, 2, 3, and 4 are all the possible values. For here we've got the frequency. How often did 0 occur? Zero occurred twice in our list. So it would have a bar with a height of 2. 1 occurred 3 times, so it would go up to there. 2 occurred twice. 3 occurred 4 times. And 4 occurred 3 times. And you can see, again, here's our highest peak. So this is a visualization of this data here as a bar graph. The highest peak tells us there's our mode. The value associated with that highest peak is our mode. Come on. Okay, so it's possible to have more than one mode. You can have data that is bimodal if there are 2 values, two most frequent values. Then there are 2 modes. And our data would be considered what we call bimodal. We saw this when we were visualizing histograms before. Just kind of has 2 humps, 2 peaks. So that's possible. You don't need to do anything with those 2 values. You don't need to like average them together. You just have more than one mode. It's possible to have more than one mode. So keep that in mind. If you had a picture like this, and there was one peak, and then we had another peak that was the exact same height, And both of these two things were the exact same maximum frequency here. So we have frequency over here, and here we have our values. We just have two different modes. And we would record both of these values, whatever these values are here and here. Those two values would both be modes. We don't try to combine them at all. We just have two different modes. Okay. So we've got our three different approaches for finding the center of our data. Why do we need three approaches? So why do we have three different measures of center? Well, each kind of suits a specific purpose. The mean is going to be the most common. It's the one that you will have dealt with the most. For example, in a class, when you take an exam, it's typically one of the things your instructor will tell you when they hand back exams. The class average was, whatever, a 74. They'll give you that mean. The others also show up in various situations. It turns out median, for example, often shows up in the context of money. And let me give you an example for why. So, let's think about an example where we're talking about incomes. And let's say that we took the 30-odd people in this class and we recorded everybody's income, and we wanted to find sort of the middle income of people in the class. So if we take 30 people's incomes, we could compute the mean. If we're talking about that being our entire population, maybe I would use mu. And I would take the first income of the first person, so income number 1 plus income number 2 plus ... all the way up to the end, the 30th person. So income number 30. And I would take those and I would divide by, take those and divide by 30 and get a result. And let's just say, for sake of argument, let's say that this maybe worked out to be, I don't know, $20,000. So, hypothetically, $20,000 is the average income of the person in the class. We've got some people that make zero money because they're just full-time students. We've got some people that have full-time jobs, and this is the only class they're making. Maybe they make $40,000, $50,000, $60,000 a year. And once we average them all together, we wind up with $20,000 a year. And that's our average in this case. But what if we add in an extra student? Let's add in Jeff Bezos or a Bill Gates or somebody that's super, super rich. So all capitals rich, like billions of dollars. So that means that student number 31, or sorry, income number 31, I should write, income number 31, let's say that it's 30, for sake of argument, $31 billion a year. That, again, this is a Jeff Bezos or Bill Gates type person. What happens when we add in that income? What happens to the mean? So now I'm adding in all those incomes, income 1 plus income 2. And again, these are just placeholders for the different students. They're placeholders for numbers. Maybe this one's $0 and this one's $15,000 and this one's $60,000. We're adding up those same values which I haven't specified, I'm just ballparking, but then we're adding in to that number this last one here, which is going to be $31 billion. And now, instead of dividing by 30, we need to divide by 31 because we have that one extra income over here. So this is really the only change that we've added in, and then this number is ever so slightly changed down here. Well, let's think about this. If there were, if this top income, average income, worked out to be $20,000, and that was the average of these 30 people, if I wanted to know what they all added up to, what did all the incomes add up to, I could figure out what the sum of all these things is by just undoing the division by 30. If I multiplied both sides by 30 to undo this division, and I would multiply this by 30, that would give me $600,000. The total incomes of everybody in the class, hypothetically, was $600,000, but that was split 30 ways, so that the average was really only $20,000. Does that make sense? Hopefully. Over here, that means that these first 30 numbers that we added up, which are the same numbers that we added up here, they add up to like $600,000, which is a lot of money until you start splitting it 30 ways. Then we're adding in this 31 billion to this 600,000. And this 31 billion is so much more than 600,000. We basically don't even care about the 600,000. We take this number, who cares about it, 600,000. What we've really got up here, right, these are basically just almost, decimals compared to the 31 billion that we've got here. So we take our 31 billion plus chump change, which is all the rest of our incomes combined, and we divide by 31. And what do we get out of this? When we do that division, we are going to get an average of $1 billion. And what it's telling us is our incomes haven't changed. All that changed was we added this one very wealthy student to the class. So which one is more reflective of how the average student in the class is doing? Is the average student making about $20,000, or on average is the average student a billionaire? And the reality is, we're not all billionaires. Throwing this one outlier in really skewed the mean, and it made it look like we're all much, much richer than we actually are. So this is an idea. The mean is easily skewed by outliers. This $31 billion right here is what we might call an outlier. And we'll formally define the concept of an outlier later in a later section, coming up soon. But the mean is skewed by outliers. What about the median? So what if we had, instead of finding the mean for these two lists, we'd found the median? Well, in that case, all it would require us to do is sort the incomes from smallest to biggest. So it would be, exercise in shame. If we were doing this in person, we'd line everybody up from poorest to richest. And then we'd find the middle person in that row of people. And we'd see how much they make. And that would be the median. So if we lined up the 30 people, found the middle, it would be somewhere between the 15th and 16th person. If we average their two incomes, that would give us the median. It would be the halfway point between the 15th and 16th person. And if we added in Bill Gates over here and did the same thing, now instead of 30 people in a row, we now have 31 people in a row, with him being way over at this end, the richest. And we still, again, go find the halfway point. And now the halfway point, instead of occurring halfway between the 15th and 16th person, as it did when there were 30 people, now it would just occur at the 16th person. Right? I would take 31, I would divide it by 2, I'd get 15.5, and I'd round that up to 16. And so instead of averaging the 15th and 16th person's incomes together to get the median, we would just look at only the 16th person. And probably it wouldn't change that much. So in this case, the fact that we have this guy that's a multi-billionaire in our list doesn't really affect the median very much. It just shifts over by half a person in our list. So the median is what we call resistant to outliers. It's not affected by them much. And so this is what dictates when we should use which of these two measures of center. If there aren't outliers, the mean is a great thing to use. If there are outliers, oftentimes we're going to be more interested in the median. And when it comes to money, there's typically outliers. That's the reason that money is one of the things that often we'll use the median on. If you hear somebody report about the national incomes, typically what's reported is median income as opposed to mean income. And it's because there are outliers. There are people that make lots more money than most people, and it skews the mean up and makes the average person look richer than they actually are. In fact, if you look at the national statistics and you look at the mean versus the median, I believe the median household income is somewhere in like the $55,000 range, whereas if you look at the mean, it's more like $80,000. It makes everybody look much richer than they are, and it's not because they're richer, it's just because there's a handful of people that make a ton more money, and that skews the mean upward. So keep that in mind. So whenever we have outliers, so if no outliers, we'll typically use the mean. If there are a bunch of outliers, oftentimes it will be better to use the median if our data set is skewed in some way. And so we'll talk about how outliers affect whether a data set's skewed down the line in just a little bit. We'll talk about the skew of a data set. In fact, we saw pictures of that in the section where we were talking about histograms. So I'll come back to this in just a minute. And then if we just have an image, if we only have a histogram, we'll often use the mode to figure out our center, because that way we don't have to do any math. You can literally just look at the picture, find the tallest peak, and say, oh, that's the mode. So the mode really typically only gets used when we're visualizing our data. It's not very useful mathematically otherwise. We don't use it much when we are just given a list of actual numbers. So how do these relate to skew? This can be the last topic before we move on. So what I've just suggested is that if we've got a data set that looks like this, we said that this data set would be skewed to the right. And this was back in section 2.2 when we were looking at pictures of histograms. Where would the mean and the median be in a picture like this? Well, the mode is really easy to find, right? This is the whole point. The mode is very easy to find. It's the tallest one. But where is the mean and where is the median? I don't know exactly where they are. I'd have to figure out where they are based on these values here and using this histogram to kind of recreate the entire list of numbers. So you will have a homework problem kind of like this where you need to reconstruct the actual original list. And I can show you how to do that problem on the calculator at some point. Say that this is the number maybe like 0 down here, and then 1, 2, 3, 4, and so on. And we would take into account the frequencies and say, oh, there's 2 zeros, so our list looks like 0, 0. Then it looks like there's 4 ones, 1, 1, 1, 1. And then it looks like there's however many 6. So if these are the frequencies over here, maybe there's 6 2s, so 2, 2, 2, 2, 2, 2. There's 6 of them. And so on and so forth. We're recreating the original list of numbers from the graph by counting how many zeros are there. There's 2 of them. How many 1s are there? There's 4. How many 2s are there? There's 6. How many 3s are there? There's 5. 4 4s, and so on and so on. And we would generate this list and be able to compute the mean and the median. But I do know that visually, if the median is maybe right here, let's just guess. I'm not saying this is exactly where it is. I'm just saying, let's just, for sake of argument, let's pretend this is where it is. I know that the mean is going to be further to the right, and it's going to be skewed to the right because of these outliers that sit on the right end. These are kind of what we think of as the outlier values. They're far from where the rest of the data is, and there's not very many of them. These things don't really affect the median all that much, but they are going to affect the mean, and they're going to skew it to the right. So how do we know if something is skewed right? If I just give you, instead of a picture of a histogram, if I just told you what the mean and the median are, something will be skewed right whenever the mean is greater than the median. Right? The mean is greater than, or another way to say that would be the mean is to the right on our number line of the median. And that's what we're showing here. The mean is greater than, right? It's over here by 4 than the median, which was over by 3. Another way of saying that is the mean is to the right. So when something is skewed right, the mean is greater than the median. If something were skewed left, if those outliers were over here on the left, then the mean would be to the left of the median. And so we would have this. If something was skewed left, we'd have that the mean would be less than the median. Or another way of saying that would be that the mean is to the left of the median in our picture. And if the mean and the median are right on top of each other, that typically means that our data set is pretty much symmetric. So if the mean is approximately the same thing as the median, if they're the same, that implies that our data set is symmetric. So without actually showing you a picture, if I just tell you where the mean and the median are, you should be able to determine whether a data set is skewed to the right, skewed to the left, or roughly symmetric. So for example, if we saw that the mean was some number, say 42, and the median of our list of numbers, some hypothetical list of numbers, was 35. Would this data set be symmetric or skewed left or skewed right? Well, I know it's not going to be symmetric because these two numbers aren't approximately the same. Maybe if it was 42 and 42 and a half, or 42 and 41 and a half, or something like that, if they were really close, I'd say, oh, that's pretty close to symmetric. But in this case, they're pretty far apart. And which one is greater than or less than the other? Well, in this case, the mean is greater than the median. So in this case, the mean is the larger number. So the mean is greater than the median. And because the mean is greater than the median, that also means that the mean is further to the right. And that must be where the tail is. The tail must therefore be on the right. Right? The tail, our outliers, should be in the same direction that the mean is. So in this case, this thing is skewed to the right. Oops. It's skewed right because the mean is to the right of the median. So just keep that in mind. One way that people, a student told me they remembered this in the past, is the mean is mean, so it chases the tail. Meaning, the mean should be the thing that's closer to the tail of our data. It's always going to be out towards the tail you could think of it as chasing the tail of our data. So in this case, if the mean is greater than, it means the mean is to the right of the median, and that must mean that the tail is out in the direction that the mean is. It's out to the right, and therefore our data set is skewed right. So hopefully that helps you kind of keep this memorized. In the next video, we will be looking at measures of how spread out our data is.